Hi, everyone. My name is Amber Holdsworth, and I'm speaking to you from the district of Saanich, which takes its name from the Saanich peoples. This is also the traditional territory of the Lekwungen peoples. Lekwungen means place to smoke herring. The caretaking of forests and meadows and beaches, and particularly the care of the Gary Oak ecosystems by these peoples was instrumental in promoting ecosystem biodiversity. I acknowledge the harm and legacy that colonization have caused to these and other Indigenous peoples to avoid the replication of these patterns and allow for a community built around respecting the Indigenous peoples and ecosystems that they steward. I want to welcome you all to our session on advancing the science of marine extremes. I'm co-chairing the session with Dr. Hayley Dosser. The session will begin with a 30-minute talk from Elise Olson. The rest of the speakers will have 12 minutes with 3 minutes for questions, and I'll give a warning at the 10-minute mark for those talks. Please type your questions into the chat box on Event Mobi and not into the Q&A. And note there is a bit of a delay, so please put your questions in right away. Don't wait for the end of the talk. And with that, I will stop sharing this intro slide and invite Elise Olson to share her talk and to go ahead.
Great. Thank you, Hayley and Amber, for this opportunity to share my recent research with you here. I've just started employment with Environment and Climate Change Canada, but the work I'm presenting was done while I was an associate research scholar at Princeton University with NOAA collaborators. Oops, not changing. There, okay. Here are some figures from IPCC showing long-term trends in ocean surface temperature and pH. Whereas these figures show global means, change is spatially heterogeneous and ecosystems feel local impacts. These changing conditions, such as ocean acidification, warming, and deoxygenation, can act alone or in concert to stress local ecosystems. In this talk, I'll focus on two areas. The first is comparisons of historical variability between ESM 4.1 output and observed surface ocean time series. And that's based on a manuscript that's been accepted for publication in Earth and Space Science. And then in the second part, I'll present more preliminary results on projections of future ocean surface extreme conditions in the context of warming and acidification. So the first question we posed is, how does variability compare locally between an Earth system model and observations? We saved daily model output from GFDL's ESM 4.1 for the period 1975 to 2022 for a suite of physical and biogeochemical diagnostics. We compared the model output to observations from NOAA Ocean Acidification Program surface moorings described by Sutton et al. 2019. Stepping back a moment, I want to show you that we have confidence that the long-term trends in the model are in reasonably good agreement with a long-term observation time series from HOT in the Pacific and BATS in the Atlantic for pH. With that in mind, we would like to address questions about the variability, including how much information we gain by saving daily versus monthly model output, and can the global Earth system model constrain multiple stressor event characteristics at specific sites for marine resource management and decision making? There are challenges to answering these questions resulting from both the observation and model sides. The observations are of short duration with data gaps and have their own uncertainty. The model intrinsic variability is not constrained to be in phase with the observations, and the model only resolves features on scales greater than about 1 degree. Our approach was to compare modeled and observed variability in extremes by matching observations to the nearest model grid cell and decomposing the modeled and observed signals into a linear trend, seasonal cycle, and residual variability, the latter two of which we compared. We also supplemented direct pH measurements with calculated pH based on estimated alkalinity following procedures that were described by Sutton et al. 2016 in order to increase the temporal coverage. So in this figure, I'm showing comparisons between modeled and observed seasonal cycle amplitude on the left and residual variability, which is everything else, on the right. with the upper panels showing the sea surface temperature and the lower panels showing pH. The background is based on the model, and the small circles outlined in black represent the observations. In general, there is strong large-scale spatial agreement in variability amplitude, although the model tends to miss the highest levels of observed variability near the coasts, and also has a bias in ENSO amplitude, resulting in larger modeled than observed variability in the Eastern Equatorial Pacific. Also, in general, the residual variability, which excludes the seasonal cycle, tends to be biased low in the model for variables other than temperature, such as the pH I'm showing here. To further investigate that low variability bias, we filtered the model and observed time series by frequency band as illustrated here, comparing the modeled and observed variability at each site on scales of 1 to 7, 7 to 31, 31 to 365, and greater than 365 days. And the full results are compared in this large series of panels, which will be available shortly in the paper. However, for the purposes of this presentation, I'm going to focus on a simplified version that highlights the main findings. And from top to bottom, the rows represent sea surface temperature, salinity, and pH, and the values plotted are the standard deviation of the filtered time series on the different time scales. The modeled standard deviation is on the y-axis, and the observed standard deviation is on the x-axis. From left to right, the columns correspond to variability on scales of less than a month, variability on scales greater than a month after subtraction of the mean seasonal cycle, the mean seasonal cycle itself, and the standard deviation of the full time series is all the way on the right. The color of each circle corresponds to the model bathymetry at each location, so that shallow coastal data points are light yellow, and the red dotted lines indicate the reported uncertainty of the original observations as a point of reference. So the main points that I'm trying to get across with this figure are that the sea surface temperature shows strong agreement across all the timescales we looked at. There's some information missing if we get down to less than a week, but it's generally in on scales of a week and longer, there's very good agreement between the observations in the model. The salinity, on the other hand, doesn't agree as well on timescales of less than a month, where the observed variability is greater than what's present in the model. As for sea surface salinity, the model pH variability also tends to be biased low, particularly at high frequencies and at coastal sites. So to summarize this part, the low frequency variability tends to have similar magnitudes between the observations in the model, but the model tends to exhibit less high frequency variability than the observations. Inconsistency between the model and observed variability tends to be greatest in regions of naturally low variability, whereas shallow coastal regions tend to have the largest observed variability and also the greatest discrepancy between modeled and observed variability. Some likely reasons for this include incomplete representation of land-sea fluxes of freshwater and tracers and their temporal variability, the absence of tidal velocities from the model, and exclusion of small scale features due to the grid resolution. So now we'd like to ask, how serious are these limitations in the context of diagnosing stressor risk? So we know that short duration extreme events can have ecosystem impacts. An example of this is that Judginus crabs exposed to 10-day acidification treatments had impaired food sensing capability. So we argue that the phase of the well-represented lower frequency variability can constrain the overall likelihood of extremes. And to illustrate this, we've plotted the daily observed sea surface temperature and pH on the y-axis versus monthly filtered values on the x-axis, which is divided into terciles by the number of data points. Daily sea surface temperature conditions classified as extreme based on a 90th percentile threshold are much more likely when the lower frequency monthly anomaly is in the upper tercile compared to the lower tercile, and similarly for pH extremes in the lower tertile and below 10%. So now I'm showing some direct comparisons of estimates of the number of multiple stressor days based on modeled and observed time series. We looked at two different stressor criteria. In the first, we used a distribution-based criteria where extreme days were those in the 90th percentile or higher based on the detrended deseasonalized anomalies, or 10th percentile or lower for pH. This constrains the overall fraction of temperature stressor days and pH stressor days at each site, but we can combine the fraction of combined temperature stressor days, which isn't constrained in that way. And that's in the plot on the upper left. The model tends to overestimate the frequency of combined stressor days compared to the observations, which is consistent with the model's tendency for too negative a correlation between temperature and pH, as shown in the middle upper plot. And also with Berger et al.'s point that stressor correlation can be used to estimate a likelihood multiplication factor for multiple stressor events relative to the co-occurrence of idealized independent variables. In the lower set of figures, we applied thresholds associated with coral stress, specifically a temperature threshold of 1 degree above the local climatological maximum monthly mean, and an aragonite saturation state of less than 3. In this case, the frequency of events is not necessarily prescribed by the criteria, so we can compare individual stressor day frequencies as well as multiple stressor day frequencies in the bottom row plots. Model observation agreement is particularly strong for the aragonite saturation state criteria. In the context of this absolute threshold, model observation agreement across sites arises from the model's accurate representation of the global mean state. This also translates to strong model observation agreement in compound temperature aragonite saturation state event frequency. So to summarize this first part of the talk, the model tends to capture observed low frequency variability on monthly and longer timescales, and therefore much of the stressor event likelihood. The model does not fully capture observed high frequency daily to monthly sea surface salinity and surface pH variability, particularly in high variability coastal regions. There are systematic biases in stressor correlations, which should be considered in the context of percentile-based multiple stressor event thresholds. And at least in GFDL's ESM 4.1, a fixed aragonite saturation state threshold results in low model observation bias due to strong model representation of the global mean state. And I'd like to acknowledge the support of this project from NOAA, Princeton University, and SEAMS. So now I'll move to the second part of the talk, which will be focusing on contrasting projections of stressor extremes. And from now on, I'll only be talking about results from GFDL's ESM 4.1. So we saved daily output from the last 40 years of several CMOS scenarios, as well as the historical period. And I'll focus on comparisons between the historical period and two scenarios, SSP 1 2.6, which includes fairly aggressive mitigation policy and restricts warming to 2 degrees Celsius, and SSP 3 7.0, which combines no additional climate policy beyond current commitments with medium to high emissions. Both scenarios are outside of the 2.2 to 3.5 degrees Celsius warming range that has been cited as more likely than not. This figure here shows the evolution of the global mean maximum monthly temperature to give an idea of where these two scenarios, which are denoted with the arrows, fall in relation to other CMIP6 scenarios. So they're not the most extreme scenarios, but they do sort of bookend the region that's considered likely. To provide a little bit more context for the results that will follow, I want to first talk a little bit about the projected changes in the distributions of stressor conditions. Shown here are global mean changes in the mean, 5th, and 95th percentile variables from 1985 in the historical simulation to 2081 in the future projections under SSP 1 2.6 on the left and SSP 3 7.0 on the right. The change in 95th or 5th percentile of the stressor distribution, which is represented by triangles, can differ from the change in the mean represented by the black dots. In the global mean shown here, this is most apparent for temperature, where on average, the 95th percentile level increases even more than the change in the mean under both scenarios. In contrast, the decrease in 5th percentile aragonite saturation state is actually slightly smaller than the decrease in the mean. And just please note that that axis is reversed so that in all cases, the direction of anticipated global mean climate change is sort of up the page. Recently, Gruber et al. And Amaya et al. Have highlighted the need for clarity regarding various extreme event definitions used in the context of marine heat waves and biogeochemical extremes, pointing out some of the choices that have to be made. For instance, events may be defined based on absolute thresholds associated with organism impacts, such as aragonite saturation state below 1 or an oxygen threshold associated with hypoxia. Alternatively, extremes may be defined in relation to local variability, for instance, based on a specific percentile of a variable's distribution. Exceedance of these thresholds may or may not lead to stress, and the association with stress depends on an assumption that organisms are well adapted to typical conditions, but not to rare events. In this case, a reference period also needs to be chosen, and it may be fixed or shift forward in time to reflect adaptation to new conditions. Event definitions can be relative to or agnostic of the seasonal cycle, and additional criteria such as event duration may be included in the criteria. In the results that follow, we explore differences in interpretation arising from specific threshold choices. In the context of relative thresholds, we explore seasonally varying versus seasonally constant thresholds, as illustrated by the figure on the lower right, with a seasonally constant threshold in orange and a seasonally varying threshold, here based on anomaly relative to the mean seasonal cycle in cyan. In the seasonally varying case, events are extreme relative to the mean seasonal cycle, whereas in the seasonally constant threshold case, temperature extremes, for example, occur during the summer. We also consider a coral bleaching threshold based on degree heating weeks in which longer lasting events are by definition more severe, as well as absolute thresholds associated with aragonite saturation state and environmental hypercapnia. In this first example, we define thresholds based on a fixed 1975 to 2014 reference period and compare the frequency of extremes based on seasonally constant and seasonally varying thresholds. Each set of 4 maps associated with a different variable has seasonally constant threshold results in the upper row and seasonally varying threshold results in the lower row, with projections, for the 2061 to 2100 period under SSP 1 2.6 to the left and SSP 3 7.0 to the right. Spatial patterns in the results are dominated by differences in historical variability amplitude rather than by spatial differences in stressor change. In the seasonally constant case, the seasonal cycle amplitude is the largest factor, and this is illustrated by the dotted lines, which denote isolines of seasonal cycle amplitude. For instance, for SST under the seasonally constant threshold definition, tropical convergence zones, which are often cloudy in summertime due to convective activity, have low historical seasonal cycle amplitude and high projected extreme condition frequency. Because acidification-related extreme days are nearly ubiquitous in the fixed reference period context, spatial patterns in compound extreme days, which are shown on the right, are driven by temperature. However, sea surface temperature aragonite saturation compound extreme days are reduced in several regions under the seasonally constant threshold due to the different timing of sea surface temperature maxima and aragonite saturation state minima associated with positive correlation between aragonite saturation state and temperature. So next, I'm going to show some results based on a shifting reference period, simulating an adaptive response to changes in annual extremes. The approach is based on the adaptive framework that Logan et al. 2014 applied to coral bleaching predictions. And the choice of a 100-year window also derives from that coral-specific study. Due to data availability, monthly frequency model output was used in the calculation of the shifting baseline thresholds. In the seasonally constant threshold context, shifting thresholds were tied to the annual maximum monthly value or the or minimum due to rough correspondence with the 95th or 5th daily percentile as shown in the upper right. So we're calculating the thresholds based on the prior 100 years as showed by the yellow section of the first plot. This next set of figures shows extreme day frequency in an adaptive reference context with a layout similar to the previous slides, except now that we've added an additional set of panels to the left showing extreme day frequencies for the historical period, as well as for the two future scenarios. Under SSP 3.7.0, projected extreme day frequencies are only slightly reduced relative to the fixed reference period definition. This reflects the rapid progression of climate change relative to the chosen 100-year window throughout the 2061 to 2100 period under that scenario. In contrast, under the SSP 1.2.6 scenario, stressor conditions actually lessen over the latter part of the 2061 to 2100 period, which we'll go back briefly. That's shown in blue in these plots on this panel. And the frequency of extreme days under that scenario is actually lower in many cases than over the historical period. So that indicates that for organisms that are able to adapt on timescales consistent with the 100-year window that we considered, stressor conditions might actually be less severe in 2061 to 2100 under the SSP 1.2.6 projection compared to the 1975 to 2014 historical period. So the next set of figures are a series of maps of stressor event frequency based on thresholds motivated by known ecosystem impacts. The first is the coral bleaching threshold of 4 degree heating weeks. That's a metric that reflects both the amplitude and duration of the marine heat waves. In this case, degree heating weeks are calculated relative to a fixed historical baseline. So that in this context, coral bleaching days are more frequent during the 2061 to 2100 period under SSP 1.2.6 than over the 1975 to 2014 historical period. There's significant overlap between warm water coral locations shown on the right and the most severe coral bleaching conditions in the Western Equatorial Pacific. The second row is based on an aragonite saturation threshold of less than 3, which has been empirically associated with coral habitat extent. Under this threshold, coral reefs in the Indonesian and Southeast Asian region begin to be affected under SSP 1.2.6, and impacted reef areas are widespread under SSP 3.7.0, although areas abutting the Arabian Peninsula are among the least impacted. The next two rows reflect the frequency of aragonite under saturation at the surface and 50 meters depth, with impacts confined to coastal and upwelling areas under SSP 1.2.6, but more widespread in the Arctic and the Southern Ocean under SSP 3.7.0. And the bottom panel uses an absolute threshold of PCO2 less than 1,000 microatmospheres, which is considered environmental hypercapnia, and that threshold has been associated with effects on marine animals. And you don't start to see large-scale extreme days be widespread until except under SSP 3.7.0, but their coastal and subtropical gyre regions start to be impacted. In terms of combined stress, if we consider compound thermal and aragonite saturation state stress days, Indonesia and the Western Equatorial Pacific become a hotspot for future coral stress under SSP 3.7.0 with near constant stress conditions. But compound stress day frequencies remain low for most of that region under SSP 1.2.6. Also, if we consider instead the total number of days that are thermal or aragonite saturation stress days, many reefs experience at least one stressor 100% of the time under SSP 3.7.0, and coastal Southeast Asian regions experience stress close to 100% of the time, even under SSP 1.2.6. So to summarize this second part of the presentation, the choice of seasonally varying versus seasonally constant thresholds with extremes relative to the mean state or mean seasonal cycle impacts the geographic distribution of extreme days. Events tend to be more evenly geographically distributed when defined relative to the seasonal cycle. And a driving factor is the influence of variability amplitude over the reference period. Relative to a fixed 1975 to 2014 reference, both SSP 1 2.6 and SSP 3 7.0 projections for the 2061 to 2100 period include extreme days more than 50% of the time for aragonite saturation, hydrogen ion concentration, and PCO2 over most of the surface ocean. Relative to an adaptive threshold tied to the mean of the preceding 100 years, 2061 to 2100 extreme days under SSP 1 2.6 are projected to occur at rates similar to the 1975 to 2014 historical period, reflecting a slowing and reversal of warming and acidification under that scenario in the late 21st century. Adaptation on 50 to 100-year timescales could be realizable for some species. Logan et al. 2014 found that simulating adaptation based on a 100-year rolling climatology led to coral bleaching predictions in rough agreement with observations over the historical period. Also, plastic adaptation responses occur over a single life cycle and can persist for multiple generations through epigenetic or maternal effects. Meanwhile, genetic adaptation occurs over many generations, such that short-lived organisms may have greater adaptation success for a given rate of change. Absolute thresholds, such as aragonite undersaturation and environmental hypercapnia, are exceeded in some coastal regions under SSP 1 2.6, but are generally geographically more widespread under SSP 3.7.0. So thank you, and I'll see if there are any questions.
Thanks, Elise. That was really interesting. Interesting to see the global projections. Well, let's check if there's any questions here. Oh, Hayley has a question. Given your results, when would you recommend the use of seasonally varying versus seasonally constant thresholds?
I think that that's probably something that you need to make a decision on based on the particular ecosystem or organism that you're looking at. I mean, I can envision situations where you might care more about the seasonally constant threshold. That's what's typically used for coral. You care about the hottest days of the year. But I can also imagine scenarios where having an unusually high winter temperature might be really disruptive to an ecosystem. For instance, if there's a particular life stage that happens at that time, or thinking about things in terms of like the mismatch dynamics of ecosystems. I think that could be influenced by differences in timing of the seasonal cycle.
Thanks. I have a question. Do you think that your results imply that for acidification, at the local scales, you really need to downscale, like you can't use the global models?
I think that the observation model comparisons really pretty strongly point to the need for downscaling in coastal areas. Yeah.
Yeah, and why didn't you look at oxygen? Is it just not available in a lot of the models, or?
It was mainly an issue of time and not having the extensive data to compare to.
Okay. If there are no more questions, let's thank our speaker and move on to the next talk. Which is by me. So I'll share my screen here. Okay, and hopefully Hayley can give me a warning if I start to go over time here, if I just get way too excited. Should be in full screen mode now. Okay, so I'm going to talk to you today about some work that I've been doing with Andrew Shao and Jim Christian, looking at clustering to characterize extreme marine conditions for the benthic region of the Northeastern Pacific continental margin. So I'm using the Northeastern Pacific Canadian Ocean Ecosystem Model with biogeochemistry from Canoe. And we have a grid spacing of about 2 kilometers, which is with 75 vertical levels. And we have atmospheric forcing from Area 5 and CO2 from Mauna Loa with a mid-latitude annual cycle imposed. OBC are from Glorious and Glodap, and we have tides, and we're running from a time period of 1996 to 2019 after a perpetual spin up in 1996. On the right-hand side of the screen, I'm showing you a subset of our domain, and I'm going to be looking just at the shelf here and just at the benthic. So I'm showing you the bathymetry so you can get an idea of what that looks like. We're just using daily subsets for analysis here. The model evaluates really well, but you're just going to have to trust me on that because instead of showing you that, I'm going to tell you about a method for characterizing extremes using unsupervised clustering and relative thresholds. And so the method that we use involves first finding unique habitats using k-means clustering for apparent oxygen utilization, temperature, and omega A. Omega A being a measure of the ocean acidification, and AOU being basically the oxygen component with the temperature part removed, so we aren't double counting on temperature. We define the extremes for upwelling and downwelling seasons separately using the 10th or 90th percentile from a fixed baseline from 1986 to 2019. So Elise did a nice job of setting up this part of the talk. So you can see an example of a distribution on the bottom. And if we pick off the edges of those distributions, that's how we define our thresholds. We're going to then analyze the historical extremes for each cluster. And you can notice in the upper right, I'm showing again that subset of our domain. And in green, I'm showing you locations that we removed because we, a priori, think that the resolution isn't good enough there. So we assume that the extremes for the regions with similar conditions for oxygen acidification heat are going to be controlled by similar mechanisms. And so to divide the domain up, because it is such a large geographical region, we have a couple of different options that have been done historically. And so drawing your attention to this sort of prevailing oceanographic feature here, we have the North Pacific current bringing onshore flow. It bifurcates in our region to the California current to the current system to the south and the Alaska current to the north. Where it bifurcates varies a lot, but there have been basic physiographic classifications done with dividing the northern and southern shelf regions, but it's not exactly clear where that bifurcation should happen. Nonetheless, it's useful to use those depending on your scientific question. Emily Rubich used a machine learning approach that integrated biotic and abiotic information to define subregions or habitats within our region. You can see that here in the colored image on the bottom. But we wanted to really simplify things and just look at regions with that are sort of environments, habitats based on our 3 stressors. And so we used unsupervised clustering by temperature, aragonite saturation state, and apparent oxygen utilization. Omega A, that measure of ocean acidification, you can just think of small values as being bad for organisms, and there's a textbook cutoff between saturation and undersaturation at about 1. So looking at our clusters on the right, you can see we ended up with 6 clusters from our analysis. And you might notice that they do track fairly well with the bathymetry that we saw on the previous slide. 2 of those clusters stand out for their ecological significance, and I'm going to talk about those specifically. We have the canyons, and you can see comparing it with Emily Rubich's distinctions using that biotic information, it maps well with the troughs region, which has 10 different species associated with it. The shallows is nicely associated with the dogfish banks region, which has 13 species, as well as the other banks in purple, which show about 4 different species. So these are really high biodiversity regions, and it's not to say that the other regions aren't important as well. So I know you're going to have this question, so I thought I'd try to get ahead of it. Could we just use a depth criteria instead of the clustering approach that we used? And the answer is really that not really. So the spatial subsetting really ignores the fact that these variables can vary significantly at the same depth. And to try to show you this, I grabbed the shallowest cluster here, plotted it in purple, and the deepest depth in that cluster is 69 meters. So then I extract all the depths that are less than 69 meters in the domain for comparison. You can see that in yellow on the map. And then on the right-hand side, I'm showing the 3D space of habitats that we clustered on, the environmental variables. And you can see there's a nice tight cluster for the purple one, but the yellow one is actually spread quite a bit. Now you might say, well, what about those physiographic classifications? Maybe if you just cut it off north of 51, you would get the same correspondence. And so I did that in orange, and you can see that's not the case. And so there is a lot of variation at that same depth level. So hopefully I've convinced you that clustering is worthwhile. And now I'll show you some of the average conditions within those clusters. So on the left-hand side, I'm showing the average values in the table here. And on the right-hand side, I'm showing you the clusters again. And then I'm showing the time series for the average value in each of the clusters for oxygen, omega A, and temperature. Down here, I'm showing you the space of depth on the x-axis and density on the y-axis. And you can see there's some overlap there. So there's not a clear distinction between the depth and the isopycnals, that the ranges that are in these clusters. However, there is, it tends to be the case that you have shallow points in the shallowest clusters and deeper points in the canyons. If we look at oxygen up here, you can see we have higher values for oxygen in the shallows than the canyons, higher values for omega A in the shallows than the canyons, and a lot more variability in the temperature in the shallows. And these differing characteristics can largely be attributed to the fact that the shallows cluster is nearer to the atmosphere and feeling that stronger influence, whereas the canyons cluster is more influenced by the upwelling and downwelling cycles on the coast. So we did, because of these, big differences in oceanography between the upwelling and downwelling seasons, as well as the fact that marine organisms can be in different life stages during these seasons, we had to find these seasonal thresholds. And we used the 10th or 90th percentile from the entire time series. And so you can see the distributions from the canyons in the left column and the shallows in the right column, and the thresholds that we obtained from each of these distributions shown in the table. You can notice that in the canyons, we're very near to the hypoxic cutoff of 60 millimoles per meter cubed, and we're below omega equals 1, which indicates that the canyons might be particularly vulnerable to extreme conditions. Last thing I want to point out here is that if you look at this temperature distributions at the bottom, we see the extreme temperatures are occurring in the upwelling season in the shallows, which is in the summer, which is intuitive to us, I think. And then in the canyons, we sort of have the opposite happening. So the extremely high temperatures occur during downwelling in the wintertime, and that is again because that region is more influenced, that cluster rather, is more influenced by upwelling and downwelling than the surface inputs. So now I'm going to show you the fraction of extreme waters in each of the clusters, starting with the shallows. So as we go down, we're looking at the fraction of extreme waters in oxygen, omega A, and temperature as a function of time. You might notice, if you're familiar with the ENSO cycle, that we can see that 1998 downwelling season pop out, as well as 2014. The fraction of extreme waters for acidification is increasing over time. And because this, again, is quite a shallow region, this could just be from the increasing anthropogenic CO2 in the atmosphere. And then in the bottom, again, we can sort of pick out ENSO, especially during downwelling. For the compound extremes, and that is when we have extremes in 2 or more stressors occurring in the same grid cell at the same time, you can see the fraction of waters in the cluster that go extreme for oxygen and omega A. Typically more than 20% during upwelling season. We do experience quite a lot of extremes relative to some of the other compound extremes. Notice I changed the axis limits on the y-axis here as we go down, and you'll notice that for the triple extremes, we really only see extremes exceed 5% of the grid cells in the cluster for the marine heat wave years, so that's 2014 and 2019. Now, if we look at the canyons cluster, you can right away see a repeating pattern for both oxygen and omega A. And if we look down at the temperature, once again, I think we start to pick out on the ENSO cluster, or the ENSO variability, especially 1998. So now if I show you the compound extremes in the canyons, you can see again, oxygen and omega A tend to be the most frequent extremes that we see. And again, you see that same pattern that we saw before, which is interesting. Compound extremes, again, are quite rare with, for triple extremes, less than 5% of the waters becoming extreme. And that's really due to the fact that there aren't very many coincident extremes with temperature for this cluster. Now I'm going to show you the fraction of extremes compared to the North Pacific Gyre Oscillation Index. So I couldn't help but notice that the two regimes where we have extreme waters for both oxygen and omega A occur during the positive phase of the NPGO. Now, the NPGO, it tells you about the strength of this North Pacific gyre oscillation. So it would be an increase in the onshore flow, but it would also increase the strength of the flow southward in the California current system. And that would lead to more upwelling, which would be cooler waters, but also oxygen poor and highly acidic waters coming up into the region. So it's sort of not surprising that you might see this kind of correspondence. We did also look at relationships with other atmospheric indices, but I'm just showing you one for today.
2 minutes.
Thanks. Okay, so thanks for listening to my description of our statistical characterization of extremes for the benthic clusters in the Northeastern Pacific continental margin. We found that the direct forcing of the atmosphere in the shallows and upwelling and downwelling in the canyons strongly influenced extremes. I don't have time to point it out, but we did find some evidence for the influence of coastally trapped waves here. Large-scale indices like the NPGO are predictive of extreme conditions, which is useful. And for the shallows, the apparent increase in omega A or acidification extremes over time is likely due to increasing anthropogenic CO2 in the atmosphere. And finally, compound extremes involving all three stressors are rare. Thank you for listening. That was all for me. If there's any questions, happy to try to field them.
Hi, Amber. I had a question. I see there's one in the chat, but I wanted to just ask about the depth range of your bottom bin, the bottom water bin size. I was just kind of curious what depth range it's covering.
Yeah, it's going to vary depending on the depth of the bathymetry there. So you because we basically have a variable grid coming down from the surface, which with tighter clustering of points of the surface as you go down. So it is actually going to vary, but not a great deal. But I can't remember off the top of my head what it would be. If we were looking at like the bottom of the Pacific Ocean, like the deep bottom of the ocean, then we'd have really large grid cells. But here we thought that it wasn't big enough to really make a huge difference to our analysis. Thanks, Wiley. I hope folks heard his mic. I don't know. Then there's a question from Hayley. Can you say a bit more about those coastally trapped waves? Yeah, so what we found is that with the correlations that we looked at correlations with the large-scale climate indices, such as the PDO and NPGO, MEIV2, which represents ENSO. And we found a lot of strong, significant correlation, well, I should say weak, but significant correlations with these indices. But then when we looked at local drivers, like something like the Buchan index, we didn't see the same kind of correspondence, and that leads us to believe that it's the remote drivers which could be brought into our region via coastally trapped waves rather than the direct forcing of the local winds that would be affecting these upwelling and downwelling regimes that we're seeing. Thanks, Hayley. And with that, I think we can move on to Hayley Dosser's talk. And so if you want to go ahead and share your screen. Yeah, looks good. So Hayley's going to be talking to us about quantifying variability in the Northeast Pacific Ocean hypoxic boundary and saturation horizons from the ocean glider data along line P. So take it away, Hayley.
All right, thank you, Amber. So I am now with Environment and Climate Change Canada, but this is work that I did with Tatiana Ross and Debbie Ianson while I was with DFO. Okay, so this work focuses on the Northeast Pacific, so building nicely on what Amber was talking about. And the Northeast Pacific has been experiencing fairly serious impacts of anthropogenic climate change, including deoxygenation, expansion of the oxygen minimum zone, more frequent and severe heat waves, and ocean acidification. And I'm going to be focusing on the deoxygenation and ocean acidification pieces of that. For ocean acidification, I'm going to specifically be thinking about carbonate saturation horizons. So those are the depths below which, in simple terms, marine organisms with calcium carbonate in their shells or skeletons will experience very detrimental impacts and actually experience dissolution due to more acidified ocean waters. So on the right there, I have a diagram that I snagged showing how changes around, specifically for the diagram, seamounts have the potential to affect different species. So in this case, we're looking at hypoxia and how that hypoxic water in the oxygen minimum zone has expanded over the previous decades, reducing the amount of habitat available. Okay, so in my study, I'm using two different data sets. The first includes 30 years of DFO ship-based bottle samples that were collected along line P. So line P is a hydrographic sampling line shown in the map there. And the bottle samples I'm looking at include carbonate system variables. So they are only collected at the 5 stations shown on the map and usually collected a few times per year. Then the second data set is ocean glider data. So that's from the DFO ocean glider fleet. That fleet has been in operation for the last 5 years, traveling along line P all the way from P4 to P26, or Ocean Station Papa. And the gliders dive between the surface and about 1,000 meters depth. And for this talk, I'm only going to show results from a single glider mission that's from spring of 2022. Okay, so the research question I wanted to answer was, how does previously unresolved variability associated with small-scale spatial processes in fact affect our interpretation of interannual trends in things like deoxygenation and ocean acidification? So using that 30 years of ship-based data, people have done things like quantify interannual trends in the depth of the top of the oxygen minimum zone or the saturation horizons. But those data are only from 5 spatial locations. They don't resolve small-scale features like eddies, internal waves, or fronts. And the figure on the right, which is from Klimak et al. 2015, shows how common those small-scale spatial features are and how important they are to variability. So the top panel shows depth versus distance from the coast, and the bottom panel shows the same field, which is temperature, potential temperature, but now in an isopycnal framework. And in both cases, you can see just tons of small-scale spatial features. Okay, so moving into the interannual trends, a lot of what I'm going to be showing builds on a paper by Ross et al. 2020, which used this same 30 years of ship-based data along line P to look at specifically the aragonite and calcite saturation horizons. So that's those thresholds below which we start to have dissolution for certain marine organisms. And in the case of their paper, they used a slightly more restrictive criteria on aragonite of 0.7, which is considered a lower bound for corals. They also looked at the top of the oxygen minimum zone, so that's the upper hypoxic boundary, which I will be talking about as well. And then they looked at the bottom hypoxic boundary, so the bottom of the oxygen minimum zone. And the trends in those fields are shown in the plots on the right. So we've got depth on the y-axis and those 30 years on the x-axis. And in the top panel, the yellow is the calcite saturation horizon, the orange is the top of the oxygen minimum zone, so that upper hypoxic boundary, and the blue is the bottom of the oxygen minimum zone. And in the bottom plot, the orange separately shows that aragonite horizon. And what they found was that the saturation horizons are shoaling, they're getting shallower, and the oxygen minimum zone is expanding downwards. Okay, So for my study, I started by quantifying the temporal variability in a slightly different way, fairly simplistic. I took the data from those 5 stations along line P, the ship-based data, and I've plotted it up here in 3 histograms. So on the left, we have aragonite, the center is calcite, and the right is the hypoxic boundary. And that's the depth of the saturation horizons and the depth of the hypoxic boundary. The colors show those 5 different stations. So P4 is more coastal, P26 is more oceanic. And what we can see, first of all, is that we don't have a ton of data points, so we are not fully resolving the underlying distributions and the associated variability in these histograms. We can also see that the depths vary by about plus or minus 100 meters around the mean for each station. So we're looking at variability that we could quantify being about plus or minus 100 meters. And you'll see there are differences between stations, with the saturation horizons being deeper, closer to the coast, and everything being shallowest when we get out to Ocean Station Papa. Now, what I wanted to do was compare that temporal variability with small-scale spatial variability that we get from the ocean glider data, because it's very high resolution in the horizontal. So to do that, I'm not going to spend a lot of time on this, even though this took up the majority of the time in terms of analysis. We used a multiple linear regression model in order to estimate aragonite and calcite saturation states from the ocean glider data, because the gliders don't measure those directly. So the MLR model uses temperature, salinity, and oxygen to estimate dissolved inorganic carbon. And we combined that with total alkalinity that was estimated using a relationship based on salinity and longitude. And using the CO2-cis algorithms, we get aragonite and calcite saturation state. The model is valid from below about 100 meters to 750 meters depth. And although I'm only showing a little snippet here in the figure, it does perform very well along line P. And then jumping right into the results from that model, using the MLR and the oxygen data that we get directly from the gliders, we can look at how these 3 fields of interest vary along line P. So on the left here, we have 3 transect plots, so depth versus distance from the coast. And you can see the line P stations are indicated along the top with those little red triangles. The top plot shows aragonite saturation state, the middle plot shows calcite saturation state, and the bottom is oxygen. And the thin black lines are isopycnals, the thick black lines show our saturation horizons, and then the hypoxic boundary in the bottom plot. So then what we wanted to do is quantify the spatial variability in the vicinity of each of those 5 line P stations. So we take a slice along that transect that's 150 meters on either side of each station, and we use that to get an estimate of spatial variability around a station. And that is what is shown in that bottom plot there. So the colors show the chunk that we're taking around each station. And for P4 and P26, it's one-sided because the glider only travels between P4 and P26, not either side of those stations. Okay, so these are the results for, on the top, the ship-based data. So that's the exact histograms that I showed previously. Those give us a sense of temporal variability over that 30-year period for those 5 different stations. And then on the bottom, we've got the equivalent histograms for one single glider mission from 2022, where we are now looking at the depth of those horizons and the depth of the hypoxic boundary in the vicinity of each of those stations. So that tells us something about the spatial variability around the stations. And what is surprising is that the spatial variability, even from just this one glider mission, is comparable to the temporal variability that we saw from those 30 years of the ship-based data. We can quantify this a bit more explicitly by looking at 2 standard deviations from the mean for each of those distributions that I showed, and also by looking at the 10th and 90th percentile. I'm only showing values for the 10th percentile here because those correspond to the shallowest depths, which is what's more relevant for biology. And what we see is that the small scale processes are causing vertical motions that are as large in magnitude as the total shoaling of the saturation horizons over the last 30 years. So in that Ross 2020 paper, the trends showed a shoaling in the aragonite horizon of 36 meters over 30 years. Calcite, it was 51 meters over 30 years. There wasn't a change observed in the hypoxic boundary. And we see that kind of vertical fluctuation from small scale processes in a single glider mission. Now, that doesn't mean that these trends are invalid, but it does mean that spatial variability is important to consider when thinking about the uncertainty in the trends. So with the glider data, we're able to start defining a new normal depth range that we can compare new data against. And we're also better resolving the shallowest values. So we're getting a better sense of how to define extreme events and what truly is extreme. And I just want to finish by quickly talking about the role of isopycnal motion. So when we talk about small scale vertical motion in the ocean, a lot of that up and down motion is going to be related to the movement of density surfaces, even just with the tides, for example. So it becomes quite important to be able to separate out the variability associated with isopycnal motion from the variability from other causes. So for example, variability caused by biological activity that changes properties at a given density. So in the plot here, I'm showing all of the glider data collected along line P during that 2022 mission. And I've separated it out into the component associated with isopycnal motion in blue and the component associated with other causes in orange. So what we can see is for the saturation horizons, isopycnal motion explains about 2/3 of the small scale spatial variability. Whereas for the hypoxic boundary depth, isopycnal motion is explaining about half of the variability. So it's quite important to consider that motion, but other causes are also very important to what we're observing. Okay, so here I've talked about using this MLR model and ocean glider data in order to quantify small scale spatial variability that was previously unresolved for the Northeast Pacific. And that spatial variability basically is comparable to the temporal variability that we saw in 30 years of ship-based data. So we can still use the ship-based data to quantify interannual trends, but it's important to think about how that spatial variability affects uncertainty, and we find that it increases uncertainty by about 10 to 20% if you account for it. And we can also use the glider data to do a better job of defining what constitutes an extreme event. So for example, by considering the 10th percentile in the glider data as well as in the ship-based data. And that's going to become just increasingly important as deoxygenation and ocean acidification worsen in the Northeast Pacific going forward. And with that, I will stop and take any questions. Thank you.
Great. Thanks, Hayley. Let's see if we have any questions here for you. I kept coming up with questions and you answered them right after I thought of them, which is great. Susan had a question. She says you might answer this by the end of the talk, but in case you don't, does the glider variability equal temporal variability if you work in density rather than depth?
Yeah, so hopefully this started to answer that question. Now, there is a subtlety here that I glossed over, so I'll touch on it really briefly. When I'm talking about something like the depth of a saturation horizon, that is not exactly equal to the depth of an isopycnal. So this separation into these two components is somewhat imperfect. You just have to take the isopycnal that best matches like the average density associated with the saturation horizon, for example, and then look at how that isopycnal moves. So I think that it's a question that we can largely but not completely answer with what I've done here. And with what I've done here for the saturation horizons, the isopycnal motion actually is the more important component, whereas for oxygen, they're about equally important, which I thought was interesting. So.
Thanks. Yeah, I thought it was super interesting that you found all this variability, compared to what they look at in the trends. And I was curious if you have thoughts about how you can use these results to improve the calculation of the trends.
Yeah, that's a really good question. And that's something that I'm just kind of starting to think about in depth. But I would say that the big piece of it is using it to do a better job of estimating the underlying uncertainty in the trends. So you can incorporate this spatial variability into the estimates of uncertainty, like in that plot that I showed from Ross et al. 2020. There are little error bounds on each measurement along the trend, and also they came up with uncertainty in the trend itself. So they did a very careful uncertainty analysis. But my results can be incorporated into that type of uncertainty analysis. And then when we get new data and we want to add a new data point to that trend, we just have more context and more understanding of what that data point actually means.
Okay, great. Thank you, Hayley. There are no more questions in the chat, so I think we can move on to our next speaker, which is Wiley Evans. And you can go ahead and share your screen, Wiley, and he'll be talking about ocean acidification. The top title is Ocean Acidification is Not a Slow Burn in Some Coastal Regions, Rapid Modulation of Corrosive Conditions in the Northern Strait of Georgia. So go ahead, Wiley.
Are you looking at the presenter view or normal?
Yeah, this is still the presenter view. There you go.
Okay, perfect. Awesome. Thanks, Amber and Hayley, for giving me the opportunity to share these results with you all today. I want to start with sort of recognizing that the community as a whole has started to appreciate over, I think, the last 5 years or so, that ocean acidification isn't just a surface-focused and secular process. Here's just a couple examples. This is first from Andrea Fassbender, published last year, showing the change in PCO2 is greatest in intermediate water in the Northeast Pacific. It's the red area in the top plot. We've seen that the seasonal amplitude is growing, both from global analyses from Peter Land-Schutzner, but also from longer time series. And that's due to anthropogenic CO2 input. And we know now that climate is modulating OA intensity. And so the example I'm showing you here is from Patrick Duke from the Northeast Pacific, showing higher intensity conditions during high gyre upwelling. These processes are all happening sort of on decadal timescales. And I think what's a little bit slower to catch on is that we can have more rapid ocean acidification modulation and conditions. And this kind of relates to timescales on the order of annual to seasonal to subseasonal. And these are timescales that have been characterized by George Waldbusser and Joe Salisbury 10 years ago as carbonate chemistry weather. These are the timescales that really matter for individual organisms in terms of what they would be subjected to and vulnerable to. There's a new paper that came out at the beginning of this year from Simone Allen using data from Puget Sound that took this concept a step further and introduced the term CO2 storms, where you can have particular seasons that are very extreme relative to what we expect them to be. The example I'm showing at the bottom is 2 different Septembers in Puget Sound, and it's differences in the drivers that set up these more extreme conditions, right? And so we're going to explore this with a time series from the Northern Strait of Georgia. And this is our location. The Strait of Georgia is the northern limb of the Salish Sea, just showing you the map of where the Salish Sea is here in the Northeast Pacific. The Strait of Georgia has a number of watersheds that are draining into it. The Fraser watershed, of course, is the biggest, but we have a number of other watersheds that are ice, snow, and rain-fed systems. The larger map shows sort of the long view of the Strait of Georgia. It's about 200 kilometers long. The schematic gives you an idea of the circulation. This is from Rich Powlitz, 2007. It's an estuarine circulation. We have ocean-bound surface flow. That surface layer moves into Haro Strait, gets mixed. There's a reflux. About 60% of that water is refluxed as intermediate water. We have new intermediate water coming from the Strait of Juan de Fuca. It takes roughly about 120 days for that intermediate water to reach our oceanographic station, which is the red dot on the map. station QU39. And right adjacent to our station is ECCC weather buoy. And so the wind rows there gives you a sense of what the winds look like along the strait, which blow along axis towards the south in the summertime and towards the north in the wintertime. The picture gives you a sense of our field operations. We do Niskin bottle drops and CTD work at this site. We directly measure CO2 partial pressure and the total dissolved inorganic carbon content, and we estimate saturation states to within 4%. So I'm just going to show you data from this site. First, sort of one of the larger forcing components, discharge. This is total discharge from all the watersheds draining into the Strait of Georgia in black. The gray is the discharge from the Fraser River watershed, and discharge from all the other watersheds are in blue. And what I want you to take from that top panel is that all the smaller watersheds matter a lot more during the fall and winter when they're a much bigger contribution to the total discharge. The Fraser is certainly dominating in spring and summer. Panel below that is the salinity at Q39. You can see salinity minima when we have the spring and summer freshet, but notably in fall and winter, there's reductions in salinity when we have these big freshets from the smaller watersheds. Panel below that is the calcite saturation state. Up to now in this session, we've been talking about aragonite. Calcite is the least soluble form of calcium carbonate. When it's dissolving, every form of calcium carbonate is dissolving. And as a reminder, aragonite saturation state, or saturation state in general, is the product of calcium carbonate ion divided by the solubility product of the mineral. And when this ratio is less than 1, there's a tendency for dissolution. And in this plot, the black line marks that value. So everything within those black lines are saturation state for calcite that's less than 1. And you can see this period in 2018 through 2020 where we had exceptionally high undersaturated conditions through the water column for calcite. This is really unique. You would have to go to below 400 meters in the Northeast Pacific to find water this corrosive. And we're finding it at 50 meters in the Strait of Georgia during these years. Panel below that is winds from the Environment Canada mooring. I'm showing the power of the wind, so the wind speed cubed in gray. And then I'm showing the cumulative sum of north-south wind stress in black. And that cumulative sum starts on September 1, near the start of the storm season. In fact, we define the start of the storm season as the first day in September where we have gale force winds, and that's the red dot in that plot. And as you move through the storm season, you're accruing northward wind stress, and that curve grows positively until we're at the end of the storm season and the winds change direction and start to blow towards the south. We have an inflection, and that's the green dot. And so the duration or the time separation between the red and the green dot gives you a sense of how long the storm season was. The height of that curve gives you a sense of the intensity of the storm season or how strong the winds were overall for that year. You can tell from this plot that maybe there's a relationship between the intensity of the winter storms and how corrosive the conditions were between 2018 and 2020. In fact, there's a pretty good relationship there. So this is just shows the percentage of the water column corrosive calcite on the y-axis, storm season cumulative wind stress on the x-axis. And these 2 years, which had the greatest storm season intensity of cumulative wind stress, lowest percent of the water column calcite saturation. What's different between these years is the amount of discharge, and I'm going to come back to the point. The other key thing here is this time period 2018 through 2020 with very weak storm season conditions and very corrosive conditions overall through the water column. So how does this work? What's going on? We're going to use a Taylor series decomposition to explore this. And just as a reminder, the saturation state is a function of temperature, salinity, total dissolved CO2, and alkalinity. We're going to define an anomaly, which is the observed saturation state conditions minus a reference. The reference, as you'll see, could be a seasonal composite or mean profile. The reference is also a function of these same terms, and then we can look at the components that drive variability in this anomaly: temperature component, salinity component, TCO2, and alkalinity components. However, what we're going to do is follow a paper by Rubin et al. that produced mixing and biogeochemistry terms because TCO2 and alkalinity are both strongly correlated with freshwater conditions. So we're going to rewrite this equation as below and then solve for each one of these terms using the reference values of observed temperature for the temperature term, observed salinity for the salinity term, TCO2 and alkalinity as a function of salinity for a mixing term, and finally the biogeochemistry is the observed TCO2 and alkalinity minus that mixing term. And this is just an example of how this calculation can work for nominal changes in temperature, salinity, and TCO2. You can see the temperature term, which is, there's actually a blue line there. It's very small because it's a small addition to the overall anomaly. The salinity contribution is also small. There's a slope to that black line. It's tiny. The mixing contribution is appreciably larger, and the BGC term has the potential to be the biggest contributor. Now we're going to apply this decomposition to the seasonal cycle. So we're going to look at seasonal composite here for calcite saturation state in the upper left, and we're going to difference that from a mean profile to produce the anomaly in the upper right. And then we're going to decompose that anomaly. So this is the temperature component of that anomaly, showing the temperature composite. Here's the salinity composite, the salinity components. Both of those components are small, as we expect them to be. From that variance in salinity, we can get the mixing term, which is the panel below the salinity panel. And then finally, in the lower right, we have the biogeochemistry term. You can see they're the largest terms. We add the temperature, salinity, mixing, biogeochemistry terms together, and we subtract them from the overall anomaly, and we end up with our error, which should be close to zero, and it largely is. There's a slight bias in the surface there. What's important here is that, again, the mixing and the biogeochemistry terms are the largest, and they're opposing. And so it's the balance between these two terms that really matters for determining the anomaly. Okay, now we're going to apply this to our full-time series. So we're looking at the anomaly of the full-time series on the top. This is the time series minus the seasonal composite. And you can see these years, 2018 through 2020, that have a strong negative anomaly. Below that is the mixing term. Below that is the biogeochemistry term. Finally, the lowest panel is the average of the mixing and the biogeochemistry terms over the 50 to 100 meter depth range, with blue being the mixing term and red being the biogeochemistry term. And as a reminder, these terms becoming more positive means improving saturation state. And these terms becoming more negative means worsening saturation state. And you can see in these years, 2018 through 2020, the mixing term actually was reduced and was not able to balance the biogeochemistry term in those years. And so we ended up with strong negative anomaly and extreme calcite saturation state conditions. Both of these terms are strongly influenced by the winter storm season. So first, I'm showing you the mixing term versus the storm season cumulative wind stress. As a reminder, positive values or increasingly positive values are improving saturation state. And when we remove 2003, there's actually a really good relationship here. 2003 is an oddball. The reason why it's an oddball is shown in this lower panel. This is the storm season discharge versus the cumulative wind stress. And you can see storm 2003 had an anomalously low discharge year overall for the storm season. It was windy, but there wasn't a lot of discharge. And so the mixing term did not increase as it normally should for a strong storm season. The biogeochemistry term also is strongly related to the storm season intensity. And as a reminder, worsening, the increasing negative, an increasing negative term would be worsening saturation state conditions. Why this term is a function of the storm season intensity is related to gas exchange. And we quantify this by looking at the difference between alkalinity and TCO2. So TCO2 is going to respond to gas exchange and alkalinity is not. And the difference between those terms will grow under strong storm seasons.
3-minute warning.
Thank you. So we have here, I'm showing the 50-meter integrated difference between alkalinity and TCO2 over the storm season. And you can see as you increase the storm intensity, there's a tendency for increase in that difference. And so let's put all these pieces together and bring back that schematic from Rich. And just if we consider a strong storm season, what ends up happening is we have this mixing term that's becoming more positive. We have a biogeochemistry term that's becoming more positive. It's modifying, these are modifications of the surface layer that end up in Harrow Strait, get refluxed back as an intermediate water that's been modified and sets up better saturation state for calcite conditions in the coming year. If we have a weak storm season, it's the reverse. So just to conclude here, so we had extreme calcite saturation state conditions in the Strait of Georgia between 2018 and 2020. It's really the balance between this mixing term and the biogeochemistry term that sets up these extreme conditions. And both of these terms are influenced by the storm season. However, well, storm season cumulative wind stress is probably a good predictor for what the saturation state conditions are going to be in the coming year, as long as there isn't a divergence between how windy it is and how much discharge we get. And then finally, and I think probably most importantly, the view that OA is this slowly manifesting threat needs to be corrected. Because without recognizing that we can have these extreme conditions manifest within years, our adaptation planning is going to be probably slowed and not as effective as it should be. So I'll stop there. Thank you.
Thank you, Wiley. That was a fascinating talk. I was curious if you have the capability of looking at pH from the measurements you have, because some recent literature really shows there's differential effects between looking at aragonite and pH, and that they can have different seasonal cycles, and just curious.
I did not do the decomposition for pH, but I should have said in that time series plot, the magenta line was the extreme pH values with pH less than 7.52. And so the most extreme pHs track the most extreme calcite saturation states, if that makes sense.
Okay, interesting. Susan asks, if 2023 had less discharge, why wouldn't the December stratification, why wouldn't that decrease stratification and increase mixing?
The mixing term is entirely driven by changes in salinity. So you need to add the fresh water to develop a strong mixing term. So it is, we've had some internal discussion about this, because typically when we say mixing term, we're thinking, like Susan is thinking about mixing, and really what we mean is dilution.
Okay. Thanks for that, Wiley. There's no more questions, so we'll move on to the last talk of the morning. Susan Allen is going to talk about anomalies in the Salish Sea due to exceptionally low Fraser River flow in July 2023. What a good setup for this from Wiley. And yeah, you're in full screen mode and should be good to go, Susan. Just have to unmute yourself.
There we go. Okay, I am now unmuted, so that's a good start. Yes, so thank you, Wiley, for talking about the Salish Sea and setting us up to talk about a large anomaly that we saw last year in July 2023. So the Fraser River was incredibly low in July last year. And so this is a piece of data from the Hydrography Service. And let me take you through this. So on the left panel, we have the flow in the Fraser River from July 9th to July 23rd. The dashed line here is the historical mean. The line here is the upper quartile. The line here is the lower quartile. And the line here, this dash line, is the lowest ever previously observed. And the green line is 2023. And importantly, the Fraser River historical values go back to 1914. And so this is very extreme. It's significantly below the lowest that's ever been observed. The Fraser River was historically low, but the other rivers in the Salish Sea were not. And so over here, we take an example, which is the Hamathco River, and you can see its daily oscillations as the glaciers and snow melt, but it is hovering right around that dashed line, which is the median. So the Fraser was historically low, but the rest of the rivers were not. So that's my brief introduction. I'm going to talk a little bit about the Salish Sea, and you'll see some plots that will remind us of the previous talk. Talk a little bit about the model, and then I'll talk about what this extremely low Fraser River did in July 2023 in the Strait of Georgia, according to the model. So the Salish Sea is a semi-enclosed marginal sea, strong freshwater, dominated by the Fraser River, as you saw in Wiley's plots, and that's coming in here. The major connection to the ocean is Juan de Fuca, which is here. And I want to note that this region here, where the islands are, is a very strong mixing region. So the Fraser River is coming in just north of this very, very strong mixing region. We can also look down a thalweg. This is the deepest line through the model. And as we start here in Juan de Fuca, we can see the dense water here coming in from Juan de Fuca. This mixing region here with super strong mixing and almost vertical isohalines in this projection. And then in the very stratified Strait of Georgia here, where we're seeing very fresh water on the surface. And then we move back up to the north where Wiley was talking in another mixing region, but we're not going to focus on that so much today. This is a picture from Griffin and LeBlanc in 1990 showing that surface brackish layer in the Strait of Georgia and that very strong mixing layer in the islands. Okay, so SalishSeaCast model is a NEMO 3.6 model. It's a baroclinic model. Horizontal grid spacing is about 1/2 kilometer by 1/2 kilometer. The vertical grid spacing is one meter near the surface and gets deep, gets thick down deep at 27 meters. It's got a K epsilon GLS vertical turbulence model. And here, what happened was Rich Pelovich pointed out how low the Fraser River was, and I just went and analyzed our real-time runs. They're all available on ERDAP, so you could have done it too. And so this is just the analysis of what we saw in July 2023. Okay, coupled to that model is a biological model and a carbon model. And so we're going to talk mostly here about the biology. Importantly, we have two groups of phytoplankton, the diatoms, which grow fast and tend to dominate when conditions are good, and nanoflagellates, who are the gleaners and do better when things are marginal, and they can dominate then. We have two zooplankton boxes. We used to call them micro and meso, but we discovered that's not a very good representation of what those boxes are. Z1 are all the zooplankton that grow quickly, have short lifetime scales. Z2 are the slower, longer lifetime scales, and also zooplankton that move in and out of the pelagic system, for example, barnacle larvae. Okay, so our methods. We took the SalishSeaCast model fields from July 9th to 23rd. That's 15 days. We stopped on July 23rd because it was observed it started to rain. And then we compared the fields to the 2007-2022 climatology. I'll note this is a 17-year climatology, so it's about half a meteorological climatology, but it's what we have. And what I wanted to do also was say, is this exceptional? Maybe it's the highest ever, but how exceptional it is. And so I defined an exceptional anomaly as being larger than 2 standard deviations of the climatology from the mean climatology. Okay, so you're going to see lots of plots like these, including with some scribbles on them to illustrate points in case you're not seeing my pointer well. So the 4 panels are the climatology, 2023. Then the next panel is 2023 minus the climatology. And then that gives us an anomaly. And the last plot is the anomaly divided by the standard deviation. and it is colored yellow if it is greater than 2 standard deviations, and it's colored red if it's less than 2 standard deviations from the mean. The first plot you're seeing here is the surface salinity, and we can see even in just the salinity plot that the Fraser River was tiny, and there was a lot of salt water, specifically in the region of the Fraser River, but generally the whole southern Strait of Georgia was salty, and we can see that was an extreme anomaly in the southern Strait of Georgia. That also was linked with a negative temperature anomaly. So most of the Strait of Georgia was warm, but this region was cold, and it was exceptionally cold. And if we look at the salinity thalweg, so now we're going back to that thalweg view. So here in salinity, you can see that dense water coming in and the fresh water near the surface. Here's the anomaly, and we're seeing it salty near the surface. And we're seeing that that is exceptionally salty in the southern Strait of Georgia and extends and goes deeper into that mixing region. This also shows us why we had cold water in this region. We've increased the mixing here because the water is salty, and that has tended to bring the cold water to the surface in this region. We can also look at nitrate, and we can see that we have high nitrate in this region. It is not an exceptionally high nitrate, and I'm going to say that's because we'll see in a minute, we've got exceptional diatoms to take it up, but we do have a high nitrate anomaly here where we've increased mixing has brought more nitrate towards the surface. And then if we look now again from the top, we can see that we have very high diatoms in this region. This is July. This is well past the spring bloom. Very high diatoms in this region. You can see that in the anomaly, and this is exceptional. This is now well up above 3 standard deviations in this region. Okay, and looking at the thalweg, we also see that these diatoms are then strongly mixed down into the mixing region, and we have anomalously high diatoms down here. Now, obviously, diatoms don't usually grow down here, but they do get mixed down here from this mixing region, much stronger in 2023 because there was many more of them. And this forms a really great place for zooplankton. And so we see enhanced zooplankton. There's always a lot of zooplankton in this region because it's a good food source from this water mixed down. But in 2023, we can see it's anomalously strong, and we have anomalously high zooplankton in this region. Okay, and so we have nitrate exhausted at the surface. Oops, I thought I had a summary slide here. Okay, I guess not. We'll keep going. So now we're going to move to the northern Strait of Georgia. And you may have noticed that we actually did have a exceptional anomaly in northern Strait of Georgia. You can see it up here. As well. In the northern Strait of Georgia, the nitrate was exhausted deeper than usual at this time. And so we have less nitrate available in the north, and that was exceptional. Expanding the vertical scale, we can see at this time, the nanoflagellates dominate in the north, and they moved substantially deeper in the water column in 2023, following that nitrate down. You can see a classic dipole here with less nanoflagellates near the surface and more at depth. And it was exceptional, the number of nanoflagellates that were at depth in this region. The zooplankton took advantage of that, and you can see that they were anomalously high in this deep region here. And the larger zooplankton, generally larger, Z2, moved their distribution down to follow those Z1, which they graze on. Okay, so in summary, we had a historically low Fraser River flow in July 2023. We haven't talked about salinity anomalies that much, but salinity anomalies and strong salinity anomalies do impact the coastal ocean. The higher surface salinity, which was exceptionally high in the southern Strait of Georgia, reduced the salinity gradient and led to stronger mixing. This mixing brought cold water and brought nitrate to the surface and led to an exceptional diatom bloom. In the northern Strait of Georgia, on the other hand, the system was more stable than usual due to weak winds and high solar energy. And the nanoflagellates formed an exceptional deep chlorophyll maximum, leading to high zooplankton and deeper than usual larger zooplankton. And so we can see that this exceptional surface salinity was very localized. And that's a little different than some of the other anomalies we've been talking about in this session. Thank you.
Thanks, Susan. That was really interesting. Let's just check the chat here. So we don't have any questions online right now. Yeah, you showed me this before, but now there's some new slides in here. Yeah, I don't think I've quite wrapped my head around exactly what's happening with the changes when you change the freshwater and how that might. I don't know. Keep trying to think about what does this tell us about like future changes in the climate. Is the Fraser Glacier fret at all? Like, would we expect this to be a proxy for some future conditions, or do you have thoughts about that?
So I haven't really studied the hydrography. I know that the general feeling is that we should see the freshet move earlier in the season, and that we should have even lower low water in the summer. So this could be a look into the future. This anomaly could be a look into the future with lower fresh water in July than usual.
Okay, thanks. We have a question from Nancy Suntians. Was the estuarine circulation modified in 2023?
Nancy, good question. I haven't looked at that. Probably yes. That would be interesting to look at, but I have not done that.
Okay. Question from Elise along the same lines as Nancy's question. Do you think the Fraser River differences were responsible for the changes in the Strait of Fuca?
Yeah, that's another good question. One of the problems and one reason you might have seen some very strong anomalies in the deep Strait of Georgia as well. The boundary conditions changed in the early part of 2023. We take our boundary conditions from live ocean, and they moved from one system to another. And so there is a change there. And so with Juan de Fuca, I do not know if it's a change it's a change in the boundary conditions because the boundary conditions changed in 2023. Parker is currently running a consistent new version of Live Ocean. So the next time we run a hindcast, we should get a consistent hindcast without the change in the boundary conditions in the middle of 2023.
Nice. Okay, thank you very much, Susan. That was a really interesting talk. And thanks to all the speakers in this morning's session. I thought it was a really interesting look at the Pacific. And join us after the 15-minute break, short break. We're going to shift to the other side of the country and look at some different talks in the Atlantic. So please come back at 5 after the hour, and we'll see you then.
Thank you, Amber and Hayley, from all the presenters and the audience.